common base amplifier. This is the BJT configuration that mirrors the common gate amplifier for the MOSFET. In this case, the input is at the emitter and the output is taken from the collector. The base is here. There's a DC V bias at the base, and there's a current source. The current source and the voltage V bias. They're biasing the BJT in the active region. We show a load connected, and we're calling the R sig, we're calling it R sub small e, because it's on the emitter terminal. So the small signal model in this case, including small RO for the BJT, would look something like this. Note that the base is grounded. V pi, which is across R pi, is positive at B and negative at E. So this is R pi, base is grounded. The input is at the emitter, so this is the input. And the input resistance is Rn. And then there is the output at the collector and the load connected RL, and the output resistance R out or RO. And previously we said that if we add the letter N to the input resistance, it means that the expression for the input resistance would include some RL. So the input resistance in this case depends on the load. What we will try to do is we will try to, as much as possible, recycle. So here, we will try to, as much as possible, reuse the results from common gate. And this circuit is quite similar to the common gate circuit, but there is R pi. So I'll try to save time and effort and just use the results of common gate and kind of correct them to reflect the presence of R pi. So in the case of input resistance, for example, here, Rn, if there is no R pi, the circuit would be similar to common gate, and the result would be the input resistance would be the expression we got for common gate, which was something like RL plus RO divided by 1 plus GM RO. So this is when there is no R pi. But if you look here at the input resistance, it's the resistance looking here, which is the common gate expression when there is no R pi, in parallel with R pi, because the resistance, the input resistance of common gate would be between this node and ground. And in this case, R pi is between the same node and ground. So if I want to find the input resistance of common base, I can simply say that it's R pi in parallel with the input resistance of the common gate. So I don't need to really do any circuit analysis. When RO is very large, if this goes to infinity, then the input resistance becomes R pi over beta plus 1. Because this expression, the input resistance of common gate when RO goes to infinity, this becomes 1 over Gm. Okay, so, and we know that Gm times R pi is beta. So the input resistance becomes this very, very small Re. R pi over beta plus 1 is a very small resistor. So very small resistance, very, very small input resistance when RO is very large. On the other hand, if RO is not very large, is not infinite, the expression RO plus RL over 1 plus Gm RO can be very large, potentially, but it's in parallel with R pi. So the input resistance is always less than R pi. That's the first result for common base. It has a small input resistance, sometimes very small input resistance. For output resistance, we'll try to do the same. Also, I want to reuse the result from common gate. And the R pi is the additional resistor in this case that wasn't here. But in output resistance calculation, if I set the input to 0, whether R pi is here or not doesn't matter. Because if I set the input to 0, I short R pi. And I will get the same result as common gate. If I want to calculate R out is the output resistance when we set V sig to 0. If I set V sig to 0, and now I have Re there and R pi. But if I set V sig to 0 for R out calculation, I short this. Re and R pi become in parallel. And they behave like R sig in the common gate case. So I can easily recycle the results. If I set Vi to 0, that shorts R pi, and I get small RO, the result from common gate. And R out is similar to the MOSFET case, but instead of just one RS, now I have Re and R pi in parallel. So I use the common gate result, and here I had RS, now I have Re parallel R pi. Now, the next circuit we will study is a combination of two stages called the Cascode amplifier. And here's the MOSFET implementation of a Cascode amplifier. I have two MOSFETs now, and they're both contributing to the amplification. I had circuits with two MOSFETs before, but only one was contributing to the amplification, the other was contributing to the biasing, was acting like a current source. Now Q1 and Q2 here, the two MOSFETs are contributing to the amplification. So the input is at the gate of the first MOSFET. The input is at the gate of the first. The output is taken from the drain of the second. And there's a node in between. The drain of 1 is connected to the gate of 2. Excuse me, to the source of 2. And this is the gate of 2. The gate of 2 is connected to some DC bias, V bias. And of course, the source of 1 is grounded here. One way to analyze this, to look at this, is but we can consider this to be a combination of common source followed by common gate. So I'll take Q1, and for Q1, the input is at the gate, the source is grounded, and there's an intermediate node here, which is the drain. So I can consider this intermediate output to be taken from the drain of Q1, which means that for Q1, the input is at the gate, the intermediate output is at the drain, and the source is grounded. So this is a common source. Now the intermediate output becomes the input for Q2, and the input for Q2 is at the source of Q2 at S2. The gate of Q2 is grounded, signal ground, because it's a pure DC voltage. And the output for Q2 is at the drain. When the input is at the source, the output at the drain, and gate is signal ground, that's a common gate. So this is a common source followed by a common gate. This is a CS, common source stage, followed by a common gate stage. So common source followed by common gate, we call this combination a cascode. And it has some interesting properties. I will not consider this to be two amplifiers. I want to consider it to be just one amplifier. So the overall, I want to look at this as one stage. This is the input and the output of the whole thing. So this is my amplifier now. This is the output, this is the input, and everything that's inside, that's an amplifier. And I want to study this amplifier inside this shape. What is the input resistance? What is the output resistance? What is the gain of the overall thing? But to analyze it, since I have analyzed, I have results for common source and I have results for common gate, to analyze the cascode, I will again reuse what I have, what I know. I'll try to avoid doing new analysis. So let's do the input resistance for the amplifier. It's VI over RI. VI is at the gate of this, and there's no input current. So here's the input current for the overall amplifier, and it's 0 because the input is connected to the gate of Q1. By inspection, we can say that the input resistance would go to infinity. Output resistance. So again, let me draw the boundaries for my overall amplifier. Output resistance now. What is the output resistance for this overall amplifier? This is a small signal quantity. If I assume that the current source is an ideal DC current source, this becomes an open circuit. The I source becomes an open circuit when I'm doing signal analysis. So the output resistance would be the resistance looking down. It's actually the resistance looking down in parallel with the resistance looking up. But if this is an ideal current source, pure DC, that's an infinite resistance here because this becomes an open circuit. So I have the output resistance of the overall amplifier equal to the output resistance of this stage looking into the drain of Q2. I'm looking into the drain of a MOSFET. I remember that I had some rules for that. I had a rule that says if you're looking into the drain of a MOSFET and there is a resistance between the source of the MOSFET and ground, then you see an RXY, which is this resistance between source and ground plus small RO for the MOSFET plus GM RS RO. Is this the case here? Well, if I'm doing output resistance calculation, I set the input to 0. Every time I do output resistance calculation, I set the input to 0. So if I set the input to 0, this here would be at ground. And to find RO, I'm looking into the drain of Q2. And between the source of Q2 and ground, if I'm looking down, I'm looking into the drain of Q1 with nothing at the gate, no signal here, and nothing at the source, no signal here. I also have a rule for this. If I'm doing output resistance calculation, the input is 0, and I'm looking into the drain of Q1, I will see small RO1. This is true because in RO calculation, VI is 0. If there is an input signal, I cannot say that I see small RO1. But if VI is 0 when calculating RO, then when I look into the drain of Q1, calculating big RO, if I'm looking into the drain of Q1, while calculating RO, where I need to set VI to 0, I will see small RO1. So for Q2 now, back to the output resistance of the amplifier, I'm looking into the drain of Q2, and under this condition, there's no signal at the gate, and there is a small RO1 between the source of Q2 and ground. And therefore, we can apply the RXY formula, the rule that if you're looking into the drain of a MOSFET, Q2 in this case, and it has a resistance small RO1 between its source and ground, you will see RO2 plus RO1 plus GM2, RO2, RO1. So this will be the output resistance of the whole thing, of the cascode. Another way to get the same result, the exact same result, is to say, well, the last stage is common gate. And I have an equation for the output resistance of common gate when there is an RS. So I can get the exact same result by considering that, okay, RO is the output resistance of a common gate with RO1 being RS. And I get the expression for output resistance R out of common gate with RS included, and I get the exact same thing. So the signal source resistance of common gate in this expression is the output is the small RO1 for Q1. And of course, that's only one way to do it. The other way is to apply the rule. And I'll get the exact same result either way. So this is the input resistance, Ri infinite, Ri or Rn, that's infinite, but there's no load, there's no RL in the expression. Output resistance Ro is RO1 plus RO2 plus GM2 RO1 RO2. A side note here, if I want to find R out, in this case, for the cascode, R out is when I set Vsig to 0. So let's say there is a Vsig here, and I set it to 0. And it has an Rsig. It doesn't matter really. R out and RO in this case will be the same. The reason is that there is no input current. So Rsig is not dropping anything. And I get the exact same expression. R out of the cascode is equal to RO of the cascode. So whether you set V sig to 0 or Vi to 0, you get the same thing. This is also the case for the simple common source. RO and ROut will be the same. But it's different in the case of the common gate. RO is not the same as ROut. Okay, voltage gain for the Cascode. AVO, open circuit voltage gain. Let's call this voltage the intermediate voltage, or the intermediate output voltage between the drain of Q1 and the source of Q2. Let's call VD. This is the signal at the intermediate node. And now I want to find the gain. So again, I will open circuit the load. There's no load to open circuit here, but that's the definition of AVO. And I want to find VO over VI. So this is mathematically equal to VO over VD times VD over VI. Why did I introduce VD to find VO over VD and then VD over VI? Because the VO over VD would be the gain of Q2, and VD over VI would be the gain of Q1. And I know I have expressions for gain, for common gate and for common source. So VO over VD and VD over VI. VO over VD is the gain of the common gate stage. This is Q2. VD over VI is the gain of the common source stage. Now, because RL is infinite, the common gate gain would be also AVO of the CG, because RL is infinite. So if I want to find the gain of the common gate, that's AVO. For the common source, the gain is VD over VI. But the common source stage is loaded by the common gate. The output of the common source here is going to the input of the common gate. So there is the input resistance of common gate, which is now loading the output of common source. So one way to look at this is the common source, VI, VD, and then this is going to a new stage, which looks like, I will redraw it, this. The common gate, okay, with this at DC, and this is the final output. And the input of the common gate is at the source of Q2. So the input resistance of the next stage here would be the load on the first stage. This is something we're familiar with this, that if I have two stages, the input resistance of stage 2 would be like an RL on stage 1. All right, so the gain of the common source of Q1 would therefore be minus GM1 R prime L, where R prime L is RO1 parallel with RL on stage 1. But what is RL of stage 1? RL of stage 1 is the input resistance of stage 2. Now, luckily, the input resistance of stage 2, the input resistance of stage 2 is the input resistance of a common gate. The input resistance of a common gate when I'm doing AVO with an infinite RL, we have an equation for that. It's RL plus RO divided by 1 plus GM RO. And if RL goes to infinity, this also goes to infinity. So yeah, I had to worry about it, but then it turns out that it's infinite, and that's okay. The input resistance of common gate happens to be infinity when the CG load, when the common gate load is an open circuit. So I only have minus GM1 RO1. And of course, I have AVOCG, and I have the expression for that. So 1 plus GM2 RO2 is AVO common gate. We derived this previously, times the gain of the common source loaded by the common gate. But we only get minus GM1 RO1 when I'm doing open circuit voltage gain calculation. So this is the AVO for the Cascode. And this is an interesting number, an interesting result, because we know that GMRO for a MOSFET is a large quantity. And now we're getting an open circuit voltage gain, which is the product of two GMROs. So if each is, say, 45, then the overall is around 2000. And that's a nice open circuit voltage gain. So the cascoding allows us to increase the gain. If there is a load connected, what happens? We can repeat the calculation with the load connected, or simply say, well, I have AVO, that's AVO. I connect RL, so that's RL. And I know RO, I derived an expression for RO, so that's RO, and that's AVO. So that's the gain when I connect A in RL. Now, if you look at this expression, and if RL is not very large, you will see that the gain will drop. So if RL, say, is of the order of small RO, then the gain will drop very quickly. The open circuit voltage gain is very large, but if you connect a load which is of the order of small RO, the gain will drop very quickly. So this conclusion about large voltage gain for a cascode, this applies when either we have an open circuit at the load, or the load is a very large resistor. At high frequency, what happens? Let's see, this is the circuit at high frequency. We had a DC current source here, which disappears when I'm doing signal analysis. We had a DC voltage source here, which becomes 0 when I'm doing DC analysis. Okay, so, and we're showing an RL in general. We may have an RL. We're also showing a CL. So in general, also we may have a CL. And for the MOSFETs, we're showing the capacitors for Q1. I have CGS1 between gate here and source. I have CGD1 between gate and drain. And I have CDB1 between drain and ground. So these are the three capacitors for Q1. For Q2, I have CGS2 between gate and source. In the case of Q2, the source is not grounded, and therefore I have to consider the body, the capacitors between drain and body and source and body. So here I will see also a CSB for Q2, because S and B are not shorted. There is this CGD2 between gate of Q2 and drain of Q2, and a CDB2 between drain of Q2 and body, which is at signal ground. So it appears between drain of Q2 and ground. So all the capacitors are shown. If you look at the colors of the capacitors, let's consider the green capacitors first. All the green capacitors are from this node, which is the output of the Cascode, to ground. So first CL is from this node. This is all one electrical node. This is one node. CL is from this node to ground, and this is the output node. CGD2 is from the same node to ground also. This is ground here at the gate of Q2. CDB2 is also from the same node to ground. So the three green capacitors, this one, and this one, I can combine them, I can add them, and they become just one green capacitor between the output and ground. So instead of three, I would have only one. Let's look at the brown capacitors now. CDB1 is between this intermediate node and ground. CGS2 plus CSB2 are also between this same intermediate node and ground. And therefore, I can now take the brown capacitors and add them and replace them by just one capacitor between the intermediate node and ground. So now I have two capacitors, the green and the brown. The green is between the output and ground. The brown is between the intermediate node and ground. Then I have CGS1 between the input. This is the input, between the input and ground. And CGD1 between the input and the intermediate node. So in total, I will end up with four capacitors: the green, the brown, the orange, and the blue. So that's better than having all these capacitors all over the place. So we have four green between output and ground, right? Brown between intermediate and ground, blue between input and ground, and orange between input and intermediate. So orange is not between a node and ground. It's between two nodes, the input and the intermediate. So we will do OCTC to find the value of omega H for the Cascode, starting with CGS1. And in OCTC, I open circuit all the other capacitors, and I set Vsig to 0, not Vi. In OCTC, you set Vsig to 0. And you see that all the other capacitors disappeared. So CGS1, what does it see? What is the resistance seen by CGS1? Well, CGS1 is connected between the input and ground like this. And it's connected to this node. And on this side, there is the gate of Q1. But we know that there's no current here, and therefore there's an infinite resistance looking into the gate of Q1. Looking to the left, what do we see? Looking to the left, there is our sig. To ground. And we can quickly say that CGS1 will only see RSig to ground. Actually, it sees RSig in parallel with what it sees looking to the right, but looking to the right is an infinite resistance. So it will see RSig in parallel with infinity, which is RSig. So that's the resistance seen by CGS1. Our CGS1 would be RSig. The resistance seen by the brown capacitor. This one is interesting. So I want to find the resistance seen by these brown capacitors. And of course, we're using the small signal models here. I'm showing the MOSFETs as MOSFETs, but I'm doing small signal analysis just for to keep the circuit simple and to use the formulas that we derived previously. So here's an example. I want to find the resistance seen by the brown capacitor, which is the sum of the three. This will be the resistance looking down in parallel with the resistance looking up. Because I look up and there's a resistance to ground, and I look down and there is a resistance to ground. If I'm looking down, what do I see? I'm looking down into the drain of Q1 with no signal here, because if there's an RSig to ground, there's no signal here. So I'm looking into the drain of Q1 with no signal at the gate and no signal at the source. So I will see a small RO1. And then looking up, what do I see? This is a common gate configuration for Q2. And I'm looking into its input at the source with an RL connected between drain and ground. So here I will see an Rn of CG when an RL is connected to the common gate. And I have a formula for this. It's RL plus RO2 divided by 1 plus GM2 RO2. So what is the resistance seen by the brown capacitor? It will be this looking up in parallel with RO1. For the green capacitors, what is the resistance seen by them? So here I see RL, and in parallel with RL, I see this. So RL in parallel with, what is this? I'm looking into the output of the Cascode with nothing at the input. And therefore, this is RO of the Cascode. And again, I have a formula for this. It's RO1 plus RO2 plus GM2 RO1 RO2. So I'm always trying to use these formulas without doing circuit analysis. Just recycle the results and apply the formulas without doing direct circuit analysis. Resistance seen by CGD1, the last one, this one. This is an interesting case. And the resistance seen by CGD1 is, because this is like the CGD in the case of the common source. And when we did this calculation, then this was an RXY. So this will be an RXY Rx being this in parallel with this, which is R sig, because the resistance looking into the gate of Q1 is infinite, and Ry is this in parallel with this, which is something that we just calculated on previous slide. And Rxy would be Rx plus Ry plus GM1 in this case, Rx, Ry. So this is a summary of the results that we just derived.